Hello, in this lecture we will continue covering first-order circuits. After covering sequential switching for first-order circuits, we will learn the stability conditions for first-order circuits. Then we will learn how to solve first-order circuits for the unit step and pulse responses. And then at the end we will cover the generalized solution of first-order circuits for non-constant sources. Sequential switching occurs when a circuit contains two or more switches that change state at different time instants. Circuits with sequential switching can be solved using the methods which we have covered earlier. Here, for instance, we have a first-order circuit because we have a single 2 mH inductor. And we have two switches which change their state at different time instants, at t is equal to 0 for this one, and at t is equal to 1 for this one. Therefore, I will start with creating the equivalent circuit for t less than 0. Here in this instance, this 10 ampere current source is directly connected to the inductor, and the inductor has in parallel this 2 ohm resistor. Since this switch is open, this 2 ohm resistor does not make any effects. And we are omitting the drawing of the inductor because the circuit is already in steady state and therefore the inductor acts as a short circuit. Then in the second interval, we change the state of the switch and the 10 ampere current source is flowing through this short circuit. Therefore, it is not connected to the 2 mH inductor, and the whole circuit reduces itself to 2 mH inductor and a 2 ohm resistor. Now here there will be still current flowing over this inductor because the current over an inductor cannot change instantaneously. At t is equal to 1 milliseconds, the circuit will be disturbed again. Specifically, this 2 ohm resistor will be connected to the rest of the circuit, and we end up with a 2 ohms in parallel with 2 ohms at 1 ohm equivalent resistor, and now we need to solve this circuit. Now let us analyze all of those intervals one by one, starting with the earliest interval. When the inductor is at steady state, when t is less than 0, it will be equal to 10 amperes. And obviously, just before the switch changes its state, I0 minus, which just denotes a very small time interval before 0, will be 10 amperes as well. Therefore, I will start with this initial condition. I short circuit for this circuit in the Norton equivalent sense will be 0 amperes because there is no current source. RT is equal to 2 and the time constant will be 2 millihenries divided by 2 ohms and equal to 1 milliseconds. And accordingly, the circuit equation will be IT is equal to I0 times e to the minus t over tau. I0 is equal to 10 amperes and I have this expression here. Now, as you can see, the circuit will start from 10 amperes and will start an exponential decay after the switch changes its state. I need to calculate the amount of current over the inductor at 1 milliseconds because I will use this as the initial condition for the next step. And at 1 millisecond, I1 minus will be 10 to the e to the minus 1, and this will be equal to 3.68 amperes. So basically, in 1 milliseconds, the circuit current through the inductor decreased from 10 amperes to 3.68 amperes. Now let us look to the solution of the circuit for the last interval when t is greater than 1 milliseconds. Here the equivalent resistance is 1 ohms. I short circuit will be equal to 0 amperes because there is no current source connected to the circuit. The time constant is L over RT. L is 2 millihenries, RT is equal to 1 ohms. Accordingly, time constant is 2 milliseconds. And the initial condition which I calculated in the previous step is equal to 3.68 amperes. So I can therefore write IT is equal to IT0 3.68 times e to the minus t. But here I should just take into account that I will put a time shift operator here because the circuit will start acting this way after 1 milliseconds. Therefore, I write 3.68 times e to the minus t minus 1 milliseconds divided by the time constant 2 milliseconds as this equation. Accordingly, the complete response of the circuit will be this. And according to this, the circuit will start from 10 amperes. We'll have an exponential decay with a time constant of 1 milliseconds, and then we'll start having an exponential decay with a time constant of 2 milliseconds, and this will be the behavior of this circuit with sequential switching. So what did we do? We just solved all of those different time intervals one by one, starting with the earliest time interval, and then use the final value of the current for each interval as the initial condition for the next interval. And we use the regular circuit analysis tools for electrical circuits. Stability is a very important concept for any type of dynamical systems, including electrical systems. A whole field called control theory deals with the stability of these systems and their control. However, we will right now cover the stability of only electrical circuits. And as you might remember, the natural response of a first order circuit is x is equal to k times e to the minus t over tau. So the complete response on the other hand is written as two parts. Xt is equal to the natural response of the system due to the initial conditions plus the forced response of the system due to the inputs. When there is no forced response, in other words, the input to the circuit is 0, and if the tau time constant is greater than 0, then the natural response goes to 0 as t goes to infinity. We call these type of circuits stable. These stable circuits only dissipate energy over time and therefore do not accumulate high amount of energy and are therefore stable. Now, how can it be a circuit unstable? Tau is equal to L over RT and tau is equal to RT times C. Obviously, a capacitance or inductor cannot have a negative capacitance or inductance value. However, this RT can be negative. How? Remember, RT is not the regular resistance, but it is the equivalent resistance of the circuit. And if a circuit contains dependent sources, then the value of RT might be negative. Therefore, we need RT, the Thevenin equivalent resistance of the circuit, be positive such that the first order circuit is stable. So basically, if you see a circuit with a dependent source, you need to test for the stability. Is this circuit stable? Let us start our analysis for creating the equivalent circuit when t is less than or equal to 0. So I will have plus minus 12 volts, 5 kilo ohms, over which the current I is passing, and my dependent source which has the 2I current passing through it. And all of this part of the circuit will be bypassed because the switch is not closed. And here I will have my capacitance which will act as an open circuit. So therefore I can write V of t, and that will be the open circuit. So how can I solve this question? So here in this circuit, if I write the Kirchhoff's current law for this node, I will see that I is equal to 2I, and from here I will be equal to 0 amperes. And if I is equal to 0, I don't have any voltage drop over this 5 kilo ohm resistor, and V of t will be equal to 12 volts, for t less than or equal to 0, accordingly V0 will be 12 volts as well. At least the behavior of this circuit before t is equal to 0 appears to be stable because it has a constant value of 12 volts at steady state. Now I will continue with the stability analysis of my circuit for t greater than 0. So I need to find RT, but in order to find RT, I need to find V open circuit and I short circuit because this circuit has an independent dependent current source. Now let us start by drawing the circuit. Plus minus 12 volts, 5 kilo ohms, and the current, controlling current I passing through that. Here I have my 2I current, which is the dependent source. When t is greater than 0, this part of the circuit will be functional, so I have a 10 kilo ohm resistor. And for finding the V open circuit, I will leave these ports open, and here I will have V open circuit. If I were to go and do node voltage analysis for this circuit, I would define this as a reference node, and I would define this node voltage as V open circuit. Now let us write the Kirchhoff's current law for this V open circuit node. 2I is getting out, another current is getting out this way, and this I by definition is entering. Therefore, I can write this as V open circuit. I will assume that that current is going out this way as well. V open circuit minus 12 divided by 5K plus 2I plus V open circuit divided by 10K is equal to 0. Now here I need to figure out what is I. I will be simply as 12 minus V open circuit divided by 5 kilo ohms. And wherever I will see I in this equation, I will put this expression. So let's write it together. V open circuit minus 12 divided by 5K plus 24 minus 2 VOC divided by 5K plus V open circuit divided by 10K is equal to 0. Let's simplify this further. 2 VOC minus 24 plus 48 minus 4 VOC plus VOC is equal to 0. And from here I end up with minus 24 to this right side and minus VOC to this left side, and from here I find VOC is equal to 24 volts. So the first step is done. Now I will need to find the I short circuit. Okay, let's draw the circuit. Plus minus 12 volts, 5 kilo ohms, and current I passing this way, the dependent source with 2I. Now I will put this 10 kilo ohms, but even though this is closed right now, I don't have to write the 10 kilo ohms because all the current will be passing through this short circuited part. So I short circuit. So the circuit simplifies itself. I will try to solve this again using node voltage analysis. I will define here the voltage, but I see that it is directly connected over this short circuit to the reference node, so it is equal to 0 volts. Then from here I can calculate I as 12 minus 0 divided by 5 kilo ohms, which is equal to 12,000 divided by 5,000, 2.4 milliamperes. Afterwards, let us write the Kirchhoff's current law for the top node. I is equal to 2I plus I short circuit. From here, I short circuit is equal to minus I, and accordingly, I short circuit is equal to minus 2.4 milliamperes. Now I have I short circuit, I have V open circuit. I find R Thevenin simply as 24 volts divided by minus 2.4 milliamperes, and this is equal to minus 10 kilo ohms. So basically the equivalent resistance of the circuit behaves as a negative resistance. Instead of dissipating energy, it generates energy. But this is all due to this dependent source. And since RT is negative, circuit is unstable. In mathematics, we are using special functions and operators to do mathematical operations easily in a more convenient way. Unit step function is one of those. It is something which we use to represent an abrupt change in a voltage or current. Here, this expression u t minus t0 is expressing a conditional mathematical statement in which the function value is 0 when t is less than t0 and it is equal to 1 when t is greater than t0. The unit step function is a dimensionless function and it is used with other physical quantities such as voltages or currents. For instance, it can be used to represent an abrupt change in voltage. If we write Vt is equal to A plus B times U t minus t0, this means that the original value of the voltage before t0 is equal to A, and after t0, the value of the voltage becomes A plus B. This is very convenient for doing lots of different operations in electrical circuits. In electrical circuits and signal processing, a rapid change of a function can be represented mathematically using pulse signal. Actually, pulse signal is nothing else than two unit step functions combined together. For instance, if a signal has a pulse for the interval delta t between t1 and t0, we can represent it this way. Vt is equal to 0 when t is less than t0. Vt is equal to v0 in this interval between t0 and t1, and it is 0 otherwise. So as you can see, if we draw the pulse function, we just see that it is like a step, but a step function was continuing till infinity, time infinity, but here we just have another drop. This drop can be generated by using another unit step function, which also continues till infinity, like the original unit step function, however, starts with an offset. So in order to create this pulse signal, I use two unit step functions, v0 times u t minus t0, and with another sign, here you see the minus sign of the signal generator, v0 times u t minus t1. This way we can generate the pulse functions. Indeed, using the unit step function, we can use it as a Lego block with sine and cosine and other types of functions to create different discontinuous functions with different characteristics at different intervals. The output of the circuit is the inductor current I0, and we need to determine the output of the circuit for the input Vs is equal to 4 minus 8 ut. Now, I would start solving this question by drawing Vs. Here I have time. Here I have Vs as a function of time. So it has the value of 4. And at t is equal to 0, it just kind of like has a unit step function of minus 8. So the value will just drop abruptly to minus 4 volts. So, and it will continue this way. So therefore I can draw the equivalent circuit at steady state for t less than 0 and for t as t goes to infinity. For this type of circuit, we will have the solution in this form. I is equal to a plus b times e to the minus at. Now I need to find these values, constants a, b, and small letter a. So let's look at here. In this case, when I0 is 0, this will be equal to A plus B, the steady state for the t less than 0, which will also be the case for I0 at t is equal to 0. When I goes to infinity, the value of this will be, since this exponential term will decay, will be equal to A. So from here I can calculate A very easily as minus 4 divided by 20, and this is equal to minus 0.2 amperes. And in this case, I can calculate this I0 simply as 4 volts divided by 20, which is equal to 0.2. Accordingly, 0.2 is equal to A plus B, but I know A from here, so 0.2 is equal to minus 0.2 plus B, and from here I calculate B as equal to 0.4 amperes. Now the last thing to find for me is A. I will find instead the tau and finalize the solution of my question. 1 over A is equal to tau, which is equal to L over RT, and L is equal to 10 henries, RT is 20 ohms, and according to the time constant is equal to 1 over 2 seconds. And finally, for t greater than 0, I can write I0 t is equal to minus 0.2 plus 0.4 times e to the minus 2t. And for t less than 0, it will simply be the value of 0.2. So this is the final solution of my circuit. The input to the circuit is the voltage of the voltage source. Vs is equal to 7 minus 14 times ut, and we need to find the capacitor voltage V output t. So let me just again start by drawing the input to the circuit. Here I have t, here I have Vs of t. It will start with 7, and at t is equal to 0, it will jump to minus 7 and continue that way till infinity. Now let us draw the equivalent circuit when t is less than 0. I have here plus minus 7 volts, 3 ohms, and 5 ohms, and the capacitor at steady state behaving like an open circuit, and according to this will be equal to 5 over 8 times 7 volts, which is equal to 35 over 8, 4.375 volts. Now, when I go to the general solution form, I can realize that V0 will be equal to A plus B, because e to the minus at will be e to the 0 and will be equal to 1. And this will be equal to 4.375 volts. Now I will need to continue and do this analysis for the second part of the circuit when t is greater than 0. Plus minus, this time I will have minus 7 volts here, because here I have minus 7. And again the same circuits, 3 ohms, 5 ohms, and an open circuit. I am right now trying to analyze the circuit when t goes to infinity. V output will be equal to 5 over 8 times minus 7, which is equal to minus 4.375 volts. And if I just look at the circuit when t goes to infinity, V0 infinity is equal to A, and this is equal to minus 4.375 volts. If A is this, and the equation for A plus B is this, I can calculate B as 8.75 volts. Now I have A and B. I need to find A. Now 1 over A is equal to tau, and this is equal to RT times C. Here I have a small problem because I don't know what's RT, but RT is 3 ohms in parallel with 5 ohms, and this is equal to 1 over 1 over 3 plus 1 over 5, which is equal to 15 over 8, and if I am not wrong, 1.875 ohms. Now let's find A. A is equal to 1 over tau, which is equal to 1 over 1.875 ohms times 460 millifarads. And this will be, let me get some help from MATLAB, 1.16 times 1 over seconds. Now I will use this information in order to finalize my circuit solution. Finally, V out of T will be 4.375 volts for T less than 0, and it will be minus 4.375 plus 8.75 times e to the minus 1.16 times T volts for T greater than 0. This is my final solution. Let us find the response of a first order circuit for an arbitrary input. The differential equation for an RL or RC circuit has this general form. dx over dt plus ax is equal to yt. Yt can be any function. It might be a step, it might be a pulse, sinusoidal, exponential decay, etc. Let's multiply both sides of 1 with e to the power of at. I end up with this expression. When I look at this expression, using my knowledge of calculus, I realize that the left side is the derivative of d over dt xt times e to the at. And I replace this expression on the left side with this new derivative expression. Now I end up with this expression 3. d over dt times xt e to the power of at is equal to function y multiplied with e to the power of at. Now if I take the indefinite integrals of both sides, the d over dt differential operator goes away on the left side, and on the right side I end up with the integral of this expression plus a constant for integration. Now I will continue my solution further. At the end I want to find xt, therefore I can multiply both sides with e to the minus at to have the xt on the left side by itself, and then the whole expression becomes e to the minus at and integral yt times e to the at dt plus k times e to the minus at. Now let's have a closer look to this expression. This right side with k looks like the response of the first order circuits to initial conditions, and this left side, this expression here, depends on the inputs. Let's see, if I assume the input to the circuit is a constant m, what does this part become? M is a constant, therefore I can take it out of the integral, and I can simply integrate e to the at dt, and for the left side I end up with m over a, and for the second part I end up with k times e to the minus at. So basically I found the general expression for the solution of first order differential equations for arbitrary inputs, and then I found for the output for the special case in which the input is m, a constant, and the output is a constant plus an exponential decay. This green part is the forcing function, the output due to the forcing input, and this right side is the output, which is called the natural response. Let's recap. Let's remember what was the output of RL and RC circuits for constant inputs. These were exactly in the same functional form. So basically, by using this expression 5, we can find the output of differential equations of first order to arbitrary inputs and use them to solve first order electrical circuits. Forced response of a first order circuit is given by this expression. Let us assume that our input yt is equal to e to the bt, an exponential function. I plug it into that expression and I take my integral, and accordingly the result is 1 over a plus b times e to the minus at times e to the a plus bt. However, I can simplify this further by getting rid of the a terms, and the output is e to the bt over ab. Now, this is something very interesting, and this is another great property of linear systems. The input has the form e to the bt, and output has also the same form e to the bt over a plus b. So the forced response of a first order circuit is independent of the time constant of the circuit and has in general the same functional form as the forced input. Here we summarize the forced responses of first order circuits to most common forcing functions. For a constant m, the forced response is n. Of course, if there was initial energy stored in the circuit would also have a natural response, but right now we are covering only the forced responses. If the forcing function is an exponential decay or an exponential function, the forced response is a function of the same form, and that is the same for a sinusoidal input. We can write the forced response as a times sine omega t plus b times cos omega t, or we could just have written this as c times sine omega t plus a different phase phi. So we have a first order circuit with a non-constant source. Vs is equal to 10 times e to the minus 2t ut volts. And we need to find the current for this inductor. So we can start by finding the forced response for t greater than 0. This switch is open at t greater than 0. The circuit will simply be an inductor, 1 Henry's, with the current IF flowing, 4 ohms, and plus minus Vs. So I will write the Kirchhoff's current law as L di over dt plus 4 times I is equal to Vs. This will be accordingly di over dt plus 4I is equal to 10 times e to the minus 2t. I don't write u of t, the unit step, because I am already beyond t is equal to 0. Now I will right now guess my solution. I will tell that IF will be in the form of b times e to the minus 2t, a function of the same form as the forced input. Let us insert this function into this equation. So the derivative of that function will be minus 2b times e to the minus 2t plus 4b times e to the minus 2t is equal to 10 times e to the minus 2t. So from here I get 2b is equal to 10 and I find b is equal to 5. Since the only unknown in this equation is b, I found my forced response for the circuit for t greater than 0. IFT is equal to 5 times e to the minus 2t. However, still I need to find the natural response of the circuit due to the initial energy stored in the circuit at t is equal to 0. Let's first find the initial condition of inductor current at t is equal to 0. For that, before t is less than 0 at steady state, I have plus minus 10 volts. This switch is closed. And here 5 ohms. And here a short circuit over which the I is flowing because at steady state the inductor acts as a short circuit. And here a 4 ohm resistor, and the voltage source is still not active, so I can just assume that it's a short circuit. So no current will pass through this 4 ohms because they will all go through this short circuit. Accordingly, IT will be equal to 2 amperes when t is less than 0, and I0 will be equal to 2 amperes since the current over an inductor cannot change instantaneously. Now we will find the natural response for t greater than 0. The circuit will become, since this switch is open, this part of the circuit will not be considered, a simple inductor, a resistor, and some type of voltage source which is a forced input to the system, therefore will not be taken into account. And accordingly, I can find R Thevenin is equal to 4 ohms. From here, tau is L over RT, and therefore 1 Henry divided by 4 ohms, 1 over 4 seconds. And I natural t will be of the form A times e to the minus 4t. And the complete response of the circuit will be natural response plus forced response, and will be A times e to the minus 4t plus 5 times e to the minus 2t. However, I know I0 is equal to 2, and this is equal to A times 1 plus 5. And from here, I find A is equal to minus 3. And accordingly, the whole response of the circuit for t greater than 0 becomes minus 3 times e to the minus 4t plus 5 times e to the minus 2t. And this part is the natural response, and this part is the forced response. Alright, I have right now here a first order circuit with a non-constant source, and I need to find the voltage Vt over this capacitor for the non-constant source of the form 10 times sine 2t for t greater than 0, and the initial voltage over this capacitor is equal to 0 as well. Now I will find forced response of this circuit for t greater than 0. For this, I want to write the KCL for this node. This current will be entering, this current will be going out, this current will be going out, and this node voltage will be V, assuming that I have the reference node here. So what will this be? The current going out from the node A through the capacitor will be 0.5 times dV over dt, plus I will have the current passing through the resistor V over 4 is equal to 10 times sine 2t. And now I need to guess a solution for this system for the forced response. V of t will be a sinusoidal function of the form A times sine 2t plus B times cosine 2t. Now here you might wonder why we are having a cosine term even though the original forcing function here has only a sine term, because if we take the derivative of this, we will end up with some cosine terms, and we need to take those into account to solve this question. So now let's plug in this solution to here. So 0.5 times the derivative of A times sine 2t. Sine 2t's derivative will be 2 times cosine t, so I will have at the end A times cosine 2t plus cosine 2t's derivative will be minus 2 sine 2t. So I will have minus b times sine 2t. Then v over 4, a over 4 times sine 2t plus b over 4 times cosine 2t will be equal to 10 times sine 2t. Now here I have a problem. I have two unknowns, a and b, but a single equation. However, some terms in this equation are multiplied with cosine 2t, and some terms are multiplied with sine 2t. I will use this in order to solve this circuit. So let's first focus on the cosine terms. A plus b over 4 is equal to 0. For sine terms, I have a over 4 minus b is equal to 10. Let's simplify a little bit. 4a plus b is equal to 0. And here I have a minus 4b is equal to 40. So I will multiply this first equation by 4. 16a minus 4b is equal to 0. And I will add these two equations. I end up with 17a is equal to 40. From here I calculate a is equal to 40 over 17. Now I need to find b. I will use this relation. 4a plus b is equal to 0. And I have 4a by using 40 over 17 for a. 160 over 17 is equal to b minus b, which I will make it here plus and put a minus sign here. So I find my b as well. Accordingly, the forced response of the circuit will become 40 over 17 times sine 2t minus 160 over 17 times cosine 2t. This is only the first part. I will need to also find the natural response of this circuit. Okay, stay with me, don't get lost. We will now find the V natural for the circuit. V natural of t will be in the form of d times e to the minus t over tau, and tau will be equal to RT times C, which is equal to 4 ohms times 1 over 2 farads, and therefore equal to 2 seconds. So accordingly, Vn will have this functional form, d times e to the minus 0.5 t. Now, the complete response of the circuit is this. V of t is equal to d times e to the minus 0.5 t plus 40 over 17 sine 2t minus 160 over 17 times cosine 2t. Now, I know the initial condition for this circuit. V0 is equal to 0. This is equal to d plus sine 0 is 0. So this term will disappear. So it will be minus 160 over 17. From here, I can calculate d is equal to 160 over 17 as well. And accordingly, the Vt is equal to 160 over 17 times e to the minus 0.5 t, the natural response, plus the forced response of the form 40 over 17 sine 2t minus 160 over 17 times cosine 2t. Obviously, this part, the natural response, will die out, will go to 0 as t goes to infinity. And this part, on the other hand, is a sinusoidal function. It will continue oscillating as long as this force continues. And this way we finish the solution of this circuit. And as you can see, if you follow the procedure, we can solve them. But there are lots of places to make silly numerical mistakes. So you need to be very careful. After solving these first order circuits, we will continue with the solution of second order and higher order circuits.